SMPS, one is flyback SMPS and another is push-pull SMPS. So let's just revise these lectures. These two SMPS, flyback SMPS first. This we use the one switch M1 as an inverter operation, which converts this DC into high frequency AC. This is high frequency transformer. Then this high frequency AC is converted into DC by using this diode. And then after apply this filter capacitor, and then it is given to this. In this case, voltage across this switch M1 is same as the supply voltage when it is in off condition. And second is the push-pull converter, in which we use the two switch M1 and M2, which convert the DC into high frequency AC. At a time only one switch is on, M1 or M2. First we turn on the M1, so that gives the positive voltage. With this polarity here, diode D1 is coming to forward bias and D2 is reverse bias. So you get the positive voltage across the loop side. Then M2 on, M1 is off. Then you get the polarity minus plus here, so D1 reverse bias, D2 is forward bias. So again you get the positive voltage across the loop side. In short, in both the cases, when M1 on or M2 on, you get the positive voltage at the load side. It means that you continuously get the DC voltage. Here again we use the filter circuit to filter out the harmonics generated at the output of this rectifier, diode-based rectifier. And turn on and turn off of this switch M1 and M2 is decided by the duty cycle, which is generated by this control circuit. Control circuit takes the feedback from the load that sends the load voltage requirement. Based on that, they decide the duty cycle of M1 and M2. Based on that, we turn. And depending upon the frequency at which the M1 and M2 is operated, the size of the LNC is decided, the size of the filter is decided, and as the frequency of this inverter is high, it means switching frequency of the switch is high, then your size of the filter LNC reduces. The overall size of the SMPS gets reduced. In this SMPS, the voltage across each switch during off condition is 2 times supply voltage, as we have discussed in the last lecture. So voltage stress across the switch during off condition is larger as compared to the other line of the SMPS. So generally this SMPS is preferred for the low voltage application because voltage stress is very high, 2 times supply voltage. So generally preferred for the low power and low voltage application. And now we start the third SMPS called as the half bridge converter or half bridge SMPS. As we have discussed that you can use any switch like power MOSFET, BJT or IGBT. Depending upon the frequency you have to require to operate. So here you can see that the circuit diagram of half bridge SMPS with the power transistor switch. You can also make the half bridge by using the MOSFET. Both the circuits are do the same operation. In this circuit we use the power MOSFET. In this circuit we use the power MOSFET. Sorry, in this circuit we use the power BJT. In this circuit we use the power MOSFET. Okay. So let's understand the operation here. Same here, supply is 230 watt AC 50 Hz, convert into DC by using a control rectifier. You get the DC here. Before applying this DC voltage to the inverter, here you provide the capacitor of same rating. So supply voltage is Vs, so each capacitor is charged with the half of the supply voltage Vs by 2 and Vs by 2. You can see the polarity of the charge voltage like this way. So at a time again here, out of this two MOSFET M1 or M2, any one thyristor is any one MOSFET is in on condition. So first we turn on the M1 MOSFET. At this time M2 is in off condition. At this time this capacitor C1 voltage positive terminal current is flowing from M1 primary winding and then negative terminal of this capacitor. It means that across the primary winding of this transformer, voltage of C1 come across, which is Vs by 2. And this circuit is open because M2 is in off condition, so this voltage is not coming to picture. Capacitor C2 voltage Vs by 2 that come into picture where M2 is in on condition. So when M1 is on, voltage across the primary is Vs by 2, voltage of this capacitor C1. So as per this polarity at the secondary side, plus minus here at the secondary side. So positive is connected with the D1, so diode coming to forward bias, D1 is coming to forward bias, and D2 is in the reverse bias. So in this case, current is flowing from diode, this LC filter and load circuit, which is the positive voltage. Now, In the second mode, when M2 on and M1 is off, in this case, current is flowing from this positive terminal of this C2 capacitor, then this lower side of the primary, then M2 MOSFET, and then negative terminal. So in this case, M2 is on, so voltage of this capacitor C2 Vs by 2 come across the primary, and polarity is here at the lower terminal is plus and upper terminal is negative. So based on that, voltage used in the secondary side is also minus plus, minus here and plus here. So with this polarity, D2 coming to forward bias, D1 coming to reverse bias. So again, current is flowing from the secondary half, D2, LC filter, and so again you can see that the direction of current is same. As you can see, the direction of current when M1 is on, which is flowing from D1. So in both the case, current is flowing in the same direction. It means your current is DC current. So both the condition when M1 is on or M2 is on, you get the DC voltage or DC current, it means DC power. So here, what is the difference in this case? Here, voltage across the off switch that is equal to supply voltage, is Vs. Because at the time when anyone switch is on, the Vs by 2 voltage coming from the primary winding of the transformer. So when anyone switch is off, the voltage come across this switch, that is supply voltage. Let's see here where M1 is on, M2 is off. So in this condition, how much voltage across this M2 switch? So let's understand this. So here M1 is on, so it means that this positive terminal through this M2, through this M1 come at this drain terminal of M2, because this is M1 is on. So this plus Vs by 2 come here at this point, and this minus Vs by 2 of this C2 polarity comes here. So plus Vs by 2, here is minus Vs by 2, so the difference is Vs. It means same as the supply. So voltage stress across the switch during off condition is same as the supply voltage. When we see in this push-pull converter, the voltage across this switch during off condition is 2 times supply voltage. So that's why we use this type of SMPS for the low voltage application. Otherwise, you require the large voltage rating of MOSFET, and which cost is high. So generally, we prefer for this configuration for low voltage application or low power application. But now in this half-bridge SMPS, voltage across the switch is same as the supply voltage. So now we can use this type of configuration for the high voltage applications. Okay. So this is the operating principle of this half-bridge SMPS. Half-bridge SMPS name is given because at the load side you get the half of the supply voltage. Here you can see that when M1 is on, at the primary winding you get the Vs by 2, same voltage you get across the secondary, or you can say that across the load also. So at a time you get the half of the supply, so that's why it is called as the half-bridge SMPS. Okay? And this is a control circuit same based on the required voltage at the load side. That will control circuit will change the duty cycle of M1 and M2. This output terminal of control circuit 1 and 2, that is nothing but a gate terminal. It means from this terminal provide the gate bus to this both this MOSFET M1 and M2. So this is the whole operating principle of this half-bridge SMPS. Now this is the simulation of half-bridge SMPS. We will discuss this later on after completion of the theory of full-bridge SMPS. Then we will see the simulation of both the half-bridge and full-bridge SMPS. And you get this type of DC output voltage and DC output current. Now let's understand the operation of this is a detailed operation as we have discussed of half-bridge SMPS. Now let's discuss the operation of full-bridge converter. So in the full-bridge converter, again you can use the power MOSFET or power BJT based on the required frequency of operation. So here this configuration is based on the power MOSFET, sorry, power BJT, and this configuration is given for the based on the power MOSFET. Both the circuit give the same operation, just we change the semiconductor switch. Here we use the power BJT, here we use the power BJT. So again, here you can see that in this full-bridge configuration we use the 4 switch or 4 MOSFET. Again, here we use the rectifier, uncontrolled rectifier, convert AC to DC. We get the Vs voltage. Now, in this full-bridge SMPS, at a time we turn on the 2 MOSFET, M1 and M2 simultaneously. Then M3 M4 simultaneously. Here again we require the center tap transformer at the center tapping at the secondary side to diode D1 D2 filter LC, and this is a control circuit which gives a 4 output signal for all the 4 switches, which is the gate signal for all these 4 transformers. Now let's understand the operation of this 2-bridge SMPS. So first you turn on M1 and M2 simultaneously. So current is flowing from this positive terminal through M1 transformer primary winding, M2 and then negative terminal. So positive terminal comes here, negative comes here. So secondary side positive, negative, positive, negative. So in this case D1 forward bias, D2 reverse bias. So you get the output voltage that is how much? Same as the supply voltage. Because across the primary you get the same as the supply voltage. V1 is equal to Vs. So at the secondary side, 1:1 transformation ratio across each secondary. So you get the Vs here also, the same voltage you get across the load side. So based on that, this filter capacitor is also designed which can able to store the voltage up to the supply voltage. So this is the operation when M1 M2 on. So in this case you get the positive plus Vs. Now turn off the M1 M2 by force commutation and then turn on M3 M4. So in this case current is flowing from positive terminal here, M3 terminal, lower terminal of this primary winding, upper terminal, M4 on, then negative terminal. So you can see that now the direction of current is reversed from the primary. So positive polarity at the lower side, negative at the upper side. So polarity is also changed in the secondary side. So minus, plus, minus, plus. So in this case D2 forward bias, D1 reverse bias. But again you can see that direction of current is same as well as voltage is also positive. Because this terminal is positive, so here positive terminal comes, where this terminal is negative, so negative terminal comes here. So again when M3 M4 is on, again you get the positive voltage and current, means you get the DC power. Yeah. So both the case you get the DC power, or you can say the same current is flowing in the same direction, and voltage rating at a time is same as the supply voltage across the load. Here V0 is Vs when M1 M2 on, or when M3 M4 is on. So it means that you get the same as the supply voltage, so that's why it is called as the full bridge SMPS, because you get the output same as the supply. Rest of the thing is same as the half bridge. This is the control circuit. Beside the duty cycle of all these bridge. Same discussion as we have done, that is repeated here in terms of equivalent circuit. Q1 Q4 is on. Here it is given name Q1 and Q4, where here we give the name M1 and M2. So in this time you get the plus Vs here. When Q3 Q2 on, you get the again you get the plus Vs for DC voltage. So circuit diagram is same, just change the switch. So these are the operation of half bridge and full bridge SMPS. Now what is the application? So as we already discussed, the application of the SMPS like machine tool industries, security system, you know that the CCTV camera that require the power supply. In that case also we use the SMPS. In support supply with the PLC, if you see the PLC lab in our department, that also we use the SMPS for providing the DC power supply. Then obviously in personal computer, mobile charger, we also use this type of SMPS. You can see this is the circuit of SMPS. It also looks like this one. Now there are different types of SMPS available in the Indian market. Different companies make this SMPS like iPhone, Antec, Ruler, Sensonic, Unix, and Corsair. So different power rating is available. You can see the price also. Now you can see this box. This is the CPU inside this. This is the SMPS box. This is the SMPS used in the CPU in a personal computer. So these are the applications of SMPS. The next topic we study this uninterruptible power supply UPS in the next lecture. So first we start the simulation of this half bridge and full bridge. Here in the simulation we done only the half bridge and full bridge simulation. So let's try to understand how to simulate it and see the waveform of it. So you can see here, theory we have seen that provide the AC supply. Here I take the 100 volt 2 volt AC of 50 Hz. This converted into DC by using this diode rectifier. So it is uncontrolled rectifier. So this is the uncontrolled rectifier, bridge rectifier, and the output of this bridge rectifier is applied to this capacitor C1 and C2. As you can see in the circuit diagram of half bridge, we use this C1 and C2 of the same rating, so that it will charge the voltage of the same voltage. So supply voltage is Vs. So both the capacitor charge the equal voltage rating, Vs by 2 and Vs by 2. Total voltage is become Vs. So same thing here, we use the two capacitors C1 and C2 of equal rating. Here I take the rating of C1 4000 microfarad. Same C2 is also 4000 microfarad. So suppose that here voltage is Vs. So both the capacitor is equally charged by Vs by 2. Clear? And this is the IGBT. Here I use the IGBT, or you can use the MOSFET or also the transistor, depending upon the application. Here I choose the switching frequency 10 kHz or 10,000 Hz to turn on and turn off this IGBT. So this is IGBT 1, this is IGBT 2. First I will turn on this, then after turn on this. So to turn on this, must provide the pulse generator, to which you provide the gate bus. So here I want to generate the AC of 10 kHz frequency. So write down the period of 10 kHz. It means 1 divided by 10,000. So it is 1 raised to minus 2. Period of 1 cycle of 10 kHz. Then pulse width is 50%. It means that 50% of the time this IGBT 1 is on, and the remaining rest of the 50% time of this period IGBT 2, this one is on. So first pulse generator 1. Here gate pulse directly applied to IGBT 1, this one without phase delay. It means first this IGBT is on. Same way here I provide the gate pulse to IGBT 2 through the not logical operator. It means that whenever output voltage of this output signal of pulse generator is 1, it gives a 0. It means there is no gate pulse for IGBT 1, sorry IGBT 2. And when 0 output, inverted this by logical operator and convert it to 1. It will turn on for the when IGBT 1 is off condition. IGBT 1 is off after the half time of this. First half with 0 delay, this one is on, and the second half this IGBT will be on. Yes. And here to provide the isolation, I am using the linear transformer. So in the linear transformer, you can select the frequency at which you operate this IGBT. So power rating is given, frequency is given. So frequency is set 10 kHz. When you simulate this, so and when you pick this linear transformer block from the simulated, inbuilt frequency is given 60 Hz. So please write down the frequency at which you operate this IGBT. So if you suppose I operate this IGBT at 20 kHz, you must write down the 20 kHz here. Clear? And here my supply voltage is given 100 watt peak. So here I write down the 100 watt for all the 3 winding. There's 2 secondary winding, as you can see in this circuit diagram. There are 2 secondary winding and 1 primary winding. So here I take the 1:1 transformation ratio between primary and each secondary, so that each winding voltage is 100. Winding 1 parameter is primary winding parameter. Winding 2 parameter is secondary winding, this one parameter, and winding 3rd parameter is this winding. And here I assume that this transformer is ideal, so I assume that resistance and inductance is 0. So whatever power is transferred from primary side, same I get it to the load side. So assume that the transformer is lossless here to get the ideal operation of this SMPS. Same way here, magnetizing resistance and inductance also there is a 0. So this transformer is works as an ideal transformer. So these changes you must do when you select this block linear transformer. Then output of each secondary is connected to the diode 5 and diode 4 and diode 5. So when IGBT 1, this one is on, this diode will come to forward bias. When IGBT 2, that is in on condition, diode 5 is in forward bias. In both the case, it gives a positive voltage according to this. And you must provide the center typing here at the secondary side, and terminal is connected to the load. Here I take the resistive load of 100 ohm and take the filter LNC filter capacitor 100 microfarad, 100 raised to minus 6, and inductor value is 1 e raised to minus 1 means 0.1 and actually you have to design this value of LNC based on the power rating. Here I take the directly this value of LNC such a way that give me the almost pure DC. So here you can see that by using this voltmeter I measure the voltage of primary winding. By this voltmeter I measure the voltage of this secondary winding. And as you know, the switch is operated at 10 kilohertz frequency, so that output, primary winding voltage as well as secondary winding voltage is also 10 kilohertz frequency. So that we measure here by using this scope as well as by using this scope. So first parameter we measure in the scope is output voltage across this load side by using this voltage. Second parameter that is measured is load current I0. Third parameter that is the primary winding voltage, this one, which is measured by this voltmeter across the primary winding, and fourth one is the voltage across this secondary winding, which is measured by this voltmeter across first secondary winding. So let's run this simulation and check the waveform so we can understand how to get this DC voltage. So now you can see that first is the output voltage across the load side. Initially you get the transient, but in the steady state condition you get the almost constant DC. This is the output voltage. Same way output current also you get constant DC current, and this is the primary voltage, the primary transformer, primary side of the transformer, and this is the voltage at the secondary side. So if you zoom this waveform, then you can see that this is the high frequency chopping of this DC voltage given at the input side of the input. So here I zoom this part only, so you can see that at how this IGBT chops the DC voltage at a 10 kilohertz frequency. So here upside you get positive, then negative, positive, negative, positive, negative. Yeah. So because of this high frequency operation of the inverter, the size of this transformer is reduced as well as the size of this filter is reduces. So overall size of this power supply becomes less. So your whole SMPS size becomes less bulky and becomes more efficient. Because here we operate at very high frequency, so at high frequency the efficiency of the power supply gets increases. So this is all about the simulation of half-bridge SMPS. Is there any other doubt in this simulation? If you have any doubt, please ask the question. Otherwise, I start the next simulation, full bridge SMPS. Is there any doubt? Anyone? All of you? Is there any doubt? Yes or no?
No, sir.
Okay. So full bridge SMPS simulation is same like this half bridge, just we use the 4 switches. As you can see this diagram of the full bridge SMPS. Here we require the 4 MOSFET or 4 switch. The rest of the thing is as it is like a half bridge SMPS. Okay. In this SMPS we use the 2. We turn on the 2 switch at a time. Clear? M1 and 2, then M3 and 2. So let's see the simulation of full bridge SMPS. So here you can see that here I use the 4 IGBT, and you can use 4 MOSFET or transistors. Same way here I take the 100 watt peak voltage 50 Hz AC, convert it to DC by using the uncontrolled diode rectifier. Here I use the 2 capacitors, again with the same capacity 4000 microfarad, and this is also 4000 microfarad. Okay. So you can also you can use this capacitor, or you can without this capacitor also you can make this circuit simulation. The concept of this putting the capacitor is just to provide the constant DC voltage at the input of the rectifier. So here you can see that there is no center tapping is provided and this branch of the C1 and C2. Where in the case of half-bridge SMPS, from the center tapping is provided through this, provide the supply of this primary of the transformer. But here now there is no center tapping. It means whenever power supply is given from here, IGBT 1 and 2 is on. Sorry, IGBT 1 and 2, this one is on. the full supply voltage, means VS supply voltage, means both this capacitor voltage come across this primary winding. Like this way. Let's here is the positive terminal. So current is flowing from this capacitor C1 IGBT1 primary winding or transformer IGBT3 and then negative. So primary winding come across the supply voltage VS. Secondary side same supply voltage. If you take the 1:1 transformation ratio, in this case your diode full coming to forward bias, 5 reverse bias, and you get the positive VS voltage across the both. Here I again take the R 100 ohm linear transformer with the same rating, with the same frequency, 10 kilowatts, 100 volt, make the zero value of R and L, magnetizing resistors inductance to get the operation like an ideal transformer. Okay. So same like a half-bridge SMPS, just we change here, instead of 2, here I use a 4 switches, and at a time 2 switches on. The logic is same to turn on this IGBT. These two IGBT turn on at the same time, so same gate pulse is applied. So you can see same gate pulse is applied, the output of this pulse generated. Same logic, period is 1 is to minus 4, 1 upon 10,000. Means 1 is to minus 4, time period of 1 cycle. 50% duration, it means first IGBT 1 and 3 is on with the 0 delay. And then after in the next half, you can see that IGBT 2 and this IGBT is on. It is applied to this not logical operator. You can see that output of NOT is applied to IGBT 2 and this IGBT. Okay. So when IGBT 1 and 3 is off, at that time these two MOSFET, sorry, these two IGBTs unconditional. But in both the cases, you get the positive voltage at the load side, and the output voltage is same as the supply, so that's why it is called the full bridge SMPS. Otherwise, the simulation and circuit configuration is almost same like a half bridge SMPS. Just changes that you get the more power because you get the more voltage at the load side. Again, the filter capacitor here I use the 1000 microfarad, and this inductor is of 0.5 Henry. So here I increase the size of capacitor and inductor because the voltage rating is become higher. In the half bridge I get the only half of the supply voltage, so I get the almost half current. But now in this case current will increases, so that I increase the rating of this filter capacitor LNC. Now let's see the operation. Let's run the simulation. Again, I have measured the first parameter voltage across the load side. Second is the current flowing from this load resistance. Third one is the primary winding voltage, this one. And fourth one is secondary winding voltage. Same like a half bridge SMPS. So let's run the simulation and observe the waveform. Same waveform you get, just changes what. Here you can see that output voltage is near to the 100 volt DC. You not get the exactly 100 because there is some voltage drop across the diode as well as the transformer. So you get the less voltage as compared to the supply. Where you can see in this operation of half bridge SMPS, here you get the half of the supply voltage. You can see that lower than 50%, almost 48 or 49, because at a time you get the half of the supply voltage in half bridge SMPS. So that is the only difference between half bridge and full bridge, that in full bridge you get the more power or more voltage, in half bridge you get the less power or less voltage. So based on that, depending upon your application, you can use any of these SMPS. Both are give the same DC voltage, and this is a this is a waveform of primary and secondary side voltage of this full bridge SMPS. Again, if you zoom this, then you can see this high frequency chopping of this turn on and turn on of this IGBTs at 10 kHz frequency. Yeah. And so as you increase the frequency 10, 20, 30, 50, then the size of this filter or the value of this LNC reduces. So whenever you actually build this SMPS, so size of this inductor and capacitor filter that it reduces, as well as this transformer size is also reduces, and our efficiency is also increases. So this is the very advantageous features of using the SMPS as compared to the linear power supply. So out of all these configurations that we have discussed today, first is private, then push-pull, and third is half-bridge and full-bridge. So out of all these four SMPS, in full-bridge configuration, very low amount of voltage and current stress happens across the switch. So generally, in most of the applications, we prefer to use this full-bridge SMPS. So this is today's simulation about half-bridge and full-bridge SMPS. Is there any doubt to anyone in both the simulation, half-bridge or full-bridge? Yes, anyone? Or to ask the question? Any question?